Hello again, everyone. This is Savin Viswanathan from NTNU for my second presentation, where I'll be talking about Modelica component models for non-diffracting floating objects and quasi-static catenary moorings. Again, in the presentation, we will talk about the motivation behind the work, look at the history of the work that has been done till now in this direction. We will give a brief overview of the current work. We will then discuss in detail the wave-body interaction problem. We will look at the simplifications. In the case of a non-diffracting object, we will look at the theory behind the quasi-static approach to catenary mooring analysis. We will talk about the implementation of the theory to develop Modelica component models. We will look at the results of the simulation and draw our conclusions. As discussed in the previous presentation, the motivation is to carry out multi-physical simulation of systems with strong influence from hydrodynamics, to remedy the black box nature of commercial software and to reduce the burden of the cost associated with commercial software, and also to develop an ocean engineering library that would allow the ocean engineering student to check out his skills in ocean engineering. So the aim was to develop an ocean engineering library for Open Modelica. At the Offshore Mechanics and Arctic Engineering Conference in 2019, we presented a work titled Towards the Development of an Ocean Engineering Library for Open Modelica, where we compared the hydrodynamic response of a catenary-moored buoy modeled both in Open Modelica and then in Orcaflex, and we showed that the results were in satisfactory agreement with each other. In the first presentation that I gave today, we talked about Modelica component models for oceanic surface waves and depth varying current, where we identified the general requirements to be taken into consideration when developing such component models. We then looked at a simulation philosophy for ocean engineering systems. We then looked at the theory behind the regular waves. We looked at the theory behind irregular waves. We looked at the theory behind depth varying current. We looked at the algorithms that help us in defining models for regular wave, irregular wave, and depth varying current. We also discussed the results of the simulation and showed that they are in agreement with theoretical values. In the current work, we will look at the wave-body interaction problem. We will then look at the simplifications in case of a non-diffracting floating object. We will talk about a catenary mooring analysis within quasi-static catenary theory. And we will look at how the models for the non-diffracting floating object as well as the quasi-static catenary mooring is developed. Looking at the wave-body interaction problem, if we consider a body in calm water and then consider an incident wave, we see that as the wave interacts with the floating object, three things happen. Because of the change in pressure associated with the incident wave, the body responds in its 6 degrees of freedom. A part of the incident wave is reflected or scattered by the body, and the motion of the body in turn causes outgoing radiation waves. Assuming linearity, we can split this problem into two subproblems. The first problem is called the diffraction problem, where we consider the body to be fixed at its equilibrium position, and then we consider the effect of the incident and the resultant scattered waves. In the second part of the problem, we consider that the body is forced to undergo oscillations about its equilibrium position, and as a result we have outgoing waves, the radiation waves that go away from the body. This wave-body interaction problem is dealt in a bit more detail in the paper. The diffraction problem gives us what is called as the wave excitation loads, which has two components. The component due to the incident wave is called the Fruit-Kirchhoff loads, and the component due to scattered waves are called the diffraction loads. The radiation problem gives us what is called as the added mass and damping coefficients. However, if the structure is relatively small, then we may ignore the effects of diffraction and damping. Now, depending upon the contributions from inertia and drag, if there is significant contribution from inertia, as in the case of the heave motion of the cylindrical buoy, we may approximate the wave loads using Fruit-Kirchhoff loads. However, if the drag is significant and inertia is small, then we can use the Morison equation to approximate the wave loads. If we consider that at any time instant the shape of the mooring line conforms to the theoretical catenary, then we can use the catenary equations to formulate a lookup table between horizontal tension and horizontal position of the buoy, and based on this the mooring forces can then be interpolated for any location of the buoy. Looking at the fluid forces on the catenary, we can use the Morison loads to calculate the wave and current loads on the mooring line itself. We now look at the implementation of the theory to develop component models for the non-diffracting floating object. Since we have developed expressions for the wave load as well as for the mooring load, we may now specify the equations of motion, where the right-hand side of the equation of motion has contribution from the wave load as well as the mooring load. So if we look at the surge direction, we have the Morison loads specifying the fluid loads, and the mooring loads are specified by the x component of the mooring load. In the heave direction, we have the Fruit-Krylov load and the contribution from the added mass specifying the wave loads, as well as the z component of the mooring force specifying the mooring force. The added mass effect is inherent in the Morison formulation in the horizontal direction. Having thus formulated the equations of motion, we can implement it as a component model in Modelica, where we use connectors of flange type to transmit the mooring loads from the mooring component model, which we will discuss in the next slide. Coming to the quasi-static catenary mooring component model, we develop an algorithm to implement the quasi-static catenary theory, and we specify three component models, where the first component model ignores the effect of the current and the waves on the mooring line itself. The second component model considers the effect of the current while ignoring the effect of the waves on the mooring line, while the third component model takes into account the effects of both the waves and the current on the mooring line. Having thus specified component models for the waves, the current, the hydrodynamic response of the non-diffracting floating object, and the catenary mooring, we proceed to building the system model in the next slide. We now build up component models and discuss results, and the first up is a fixed cylinder in waves and current. The component model is built up by connecting the component models for regular waves, for the current, and as well as for the floating object. Inside the component model for the floating object, we set the equations of motion such that the x and z locations are held constant throughout the simulation. The wave component model and the current component model generate parameters that enable the object component model to calculate the wave and current loads at the required location. If we look at the results, we first discuss a case where we consider a current only. So the wave height in this wave component model is set to 0 and the current is slowly ramped up. We see that as the current ramps up, the Morison force also ramps up before settling at a constant value when the current stabilizes. The differences between the Modelica and Orcaflex results noticeable during the ramp-up phase is due to the difference in the ramping functions that we have used. In the second case, we consider the effect of the wave only. This is done by setting the current profile to 0 at all depths and assigning a positive value to the wave height. We see that as the wave is ramped up, again the Morison force ramps up. In this case, the mean Morison force is 0 and the wave causes the force to oscillate about this 0 position as the wave crest and trough passes over the cylindrical object. In the third case, we consider the effect of both waves and current. So in this case, we have specified a current profile and we have specified a wave height, and both are slowly ramped up. We see that in this case, the presence of a positive current offsets the mean Morison force to a positive value, and the effect of the wave is to cause this Morison force to oscillate about this mean positive value. We now discuss the case of a free-floating cylinder in waves and current. Again, the system model is built up using component models that we already developed. In this case, the cylindrical buoy component model has the full equation of motion, but since the mooring line is not connected to the flange connector, the mooring forces are taken to be 0. If we look at the results for an unmoored cylindrical buoy in waves, we see that the heave response and the surge response between Modelica and Orcaflex show good agreement. The slight difference in the surge response is due to the difference in the ramp-up phase of the wave force. If we look at the surge response of an unmoored cylindrical buoy in both waves and current. We see that again the results are in good agreement between Orcaflex and Modelica. We now discuss the results of the catenary mooring component model. In the system model, we connect the mooring line to the cylindrical object. We specify the waves and the current to 0, and then we specify the cylindrical buoy equation of motion in such a way that it gives a motion to the cylindrical buoy, and at different instants we look at the mooring loads. We see that the mooring loads are in good agreement between both Modelica and Orcaflex for different specific masses of the mooring line. However, we see that when we specify a current, the mooring line in the Orcaflex model deflects as a response to the current. But since we use the quasi-static catenary approach, the mooring line shape in the Modelica component model remains the same. We now look at the simulation results for a moored buoy in waves and current, where we consider the current loads to act on the mooring chain. The system model is built up using component models. Here we have used the component model for the catenary mooring, which considers the current loads on the mooring chain. Looking at the results, we see that when we switch off the waves and consider the surge and heave response of the buoy, they are in good agreement with Orcaflex results. When we switch on the waves and the current, we see again that the heave and surge responses are in satisfactory agreement with Orcaflex. There is a slight difference in the surge, and this could possibly be due to the fact that we consider only the current loads on the mooring chain, and also since we use the quasi-static catenary approach, the dynamic loads due to the motion of the mooring line itself is disregarded in the Modelica model. We now look at the simulation results for a moored buoy in waves and current, this time considering both current and wave loads to act on the mooring chain. Again, the system model is built up in a similar way, with the only difference being that we now use the catenary component model to account for both current and wave loads. We see that the Modelica and Orcaflex results in both surge and heave are now in agreement with slight differences, and this could be because of the contribution of the inertia of the mooring line, which the Modelica model does not capture because of the quasi-static catenary approach. We also notice that the Modelica model in this case is quite sluggish. This could be due to discontinuities in the accelerations calculated by the catenary component model in Modelica. Having looked at the simulation results, we come to the conclusion that the component models developed capture the hydrodynamic response of a cylindrical non-diffracting floating object and the mooring forces based on the quasi-static catenary approach. The Morison and Fruit-Krylov forces calculated by the Modelica model were seen to be in good agreement with the results calculated by Orcaflex. The mooring forces calculated by the Modelica model were seen to be in satisfactory agreement with those calculated by Orcaflex. The hydrodynamic response of a moored buoy in waves and current obtained from Modelica was seen to be in satisfactory agreement with results for a similar system in Orcaflex. The difference in the responses, if any, can be attributed to the inability of the Modelica model to capture dynamic effects of the mooring line. The component models thus developed were then incorporated into the preliminary ocean engineering library for OpenModelica that we developed in the earlier presentation. So the component models that we have developed for the cylindrical buoy as well as for the mooring components are now incorporated into the ocean engineering library. All the simulations discussed are available for download. The download location is specified in the paper. And thank you.